Hey, AP Chemisters, this is Mrs. Vanderlei bringing you another edition of Blankwalle video. We are in Chapter 4, which is really about solution chemistry. In Section 4.4, we're talking about molarity and moles per liter and dilutions, and we're making these solutions, and you need a solute and a solvent. Well, probably one of the most common, well, not probably, the most common solvent there is water, okay? So we're going to start this section with water properties. And why would that be important? Because how do things dissolve? Well, we have to look at water to answer that question, okay? So really, water properties has a high specific heat. That means it absorbs a lot of energy before it gets hotter. It has a high heat of vaporization, means it takes a lot of energy for it to, go from a liquid to a gas. High cohesive and adhesive forces, that talks about really the intermolecular attractions that we're going to talk about later on. So like there's a polar molecule, that's section 9.6. So those things, the fact it's a polar molecule, if you remember what that means from your first year chemistry class, that means there's an unequal distribution of electrical charge. That means it has a partial positive and partial negative. And you can see that right here. So the hydrogens are the areas of partial positive, and the oxygen is the area of partial negative. And as you know, opposites attract, so that because it has those partial charges, it's going to be attracted to things that have charges themselves, okay? Hydration, it says since opposites attract, the positive ends of water are greatly attracted to negative ions of a crystal structure, while the converse is also true. For the case of sodium chloride, sodium is your positive ion, so the negative end of oxygen will be attracted to it. Hydrogen is a positive ion, so it'll be attracted to the negative chloride. So we can talk about solubility, okay? Solubility for an ionic substance, sodium chloride is highly soluble, while silver chloride is not. So it forms a white precipitate if you were to make it. It does not redissolve in water. When the hydration attractions are greater than the crystal lattice ion-ion attractions, the compound is soluble. So there are several things going on here, okay? There is the solvent-solute interactions. So the attraction between the water and the crystal, okay? The water and the sodium chloride. There is that attraction, but there's also an attraction amongst the sodium and the chlorides. So really, solubility involves which one is stronger. Is it the attraction for the solvent and the ions of the solute, or the sections of the solute? Then it's going to dissolve. If the solute particles are actually more attracted to each other than they are of the solvent, then they're not going to dissolve, okay? And so that's what we're talking about as far as why do things dissolve and why do things not, okay? So again, here's my idea of sodium chloride. The negative oxygen will be attracted to the sodium and try to pull it away. The positive end of water will be attracted to the chlorine and try to pull it away. So because I know in my heart of hearts that sodium chloride dissolves in water, then the solvent-solute interactions are greater than the solute-solute. So here is a picture of kind of what's going on. And if you check out your Google Classroom, you'll see a video that is of really salt dissolving. And if you want to see this, which I want you to do, to watch salt dissolve, pause this, go back to Google Classroom, find the salt dissolving video, watch it, and then come back. So I'll pause this while you do that. Okay, welcome back. I hope that video was helpful. And I really do like the 3D modeling that you see in that video. It does a nice job explaining why, in this case, the salt dissolves. But keep in mind, not every ionic compound does dissolve. And it is because they're more attracted in this crystal lattice than they are than the water molecules can strip it away. Okay, let's go to the next page. We have something called covalent solubility. So this is why your alcohols and your sugars and things like that will dissolve, okay? It's still the idea of this polar, partial charges. And again, opposites attract. So if you have two polar molecules, there's going to be a partial positive and a partial negative on each molecule, and they will then be attracted to another polar molecule. So it says water can also dissolve non-ionic substances such as alcohols and sugars, among others. Alcohols and sugars contain this OH bond. I see this oxygen here. We know it's highly electronegative. It has that partial negative charge. The hydrogen will be a partial positive charge, all right, just like in water. And it makes this polarity of the actual molecules of sugar or of ethanol also. So here is our attraction. Here's my water molecule. Here's my partial negative. It's going to be attracted to the partial positive that you see right here of your ethanol. Okay, so there is that attraction. The same thing can be said of your different kind of sugars. See, look at all these OHs. Look at the OH. Look at the OH. And that same thing is going to happen. That's why that sugar is so soluble in water. That's how can you make such sweet tea, all right, because of this attraction. So problem number 24 says, describe the difference between ionic solute and a covalent solute dissolving in solvent water. So take a minute out, jot down some ideas, and I'll come back and I'll give you my ideas. Okay, well, hopefully you are back and you unpause this. And so what would be the difference? So an ionic solute has full positive and full negative charges. A covalent solute has partial charges, partial positive, partial negative. So that would be your biggest difference. Really, the biggest similarity is that they're both attracted to water for its partial negatives and partial positives, all right? But again, ionic has full charges. They are in a crystal lattice, like we saw on the prior page. Covalent substances, this is all one molecule, all right? We are not pulling apart the molecule. It's just being attracted, so the whole molecule leaves with the water, all right? But we're not pulling it apart. It says electrolyte and non-electrolyte, okay? So let's kind of take a look here. So a solution is a homogeneous mixture when the solute is dissolved in a solvent. All right, so aqueous solutions are solutions where the solvent is water. Electrolytes will conduct electric current. So let's kind of look at these pictures down here. So here is sugar. This is table sugar. And this is like the water saying, hey, here's this whole thing of C's, H's, and O's. You know, it's going to pull those molecules away from one another, but there's no charges. All right, so this will not conduct electricity because there's no positive or negative charges. A weak electrolyte would be vinegar. This is acetic acid. And so if you know anything about acids, all right, you're going to pull off an H plus. Do you see that? Here's an H plus, right where my little mouse is wiggling around. And here is the rest of the molecule of the acetate, which is a negative. All right, so if you look at this picture here, that every acetic acid loses hydrogen. Here's another one, here's another one, here's another. Now, there are 5 acetic acids, and only this one lost its charge, lost its hydrogen. So most of what's in solution is still a non-charged molecule, a covalent molecule of acetic acid. Only one out of these 5 split up to make a positive and negative charge. So the more positives and negatives you have, the more it will conduct. So really, your vinegar is a weak electrolyte. It only lights the light only weakly. All right. Oh, what a clever name. So what about sodium chloride? When it is, taking apart, when the water drags it apart, it now has these positive and negative ions floating around, all right? Those are your positive and negative charges in that solution. And that's what is used to conduct electricity. That's why you should never be in a swimming pool in a lightning storm, because a lot of the stuff in the water to keep it, quote, clean is ionic, all right? And therefore, it's going to conduct electricity. So if there's any ions whatsoever in that swimming pool, it will conduct, and you could get electrocuted, so get out, all right? And if you look at the light bulb, you will see that it is a very strong electrolyte, and the light bulb is greatly lit. So that's one way to determine the electrolytes, okay? Let's go to the next page. So we have electrolyte strength. A strong one will completely dissociate. What does it mean to dissociate? It means to split up. So we have strong acids. There are 6 of those. Strong bases, and you have group 1, group 2, and then any kind of soluble salts, all right? So why do they completely dissociate? Because the water solute interaction is greater than the solute-solute, so that the water will split off the H. The water will split off the OH. The water will split up the positive and negative ions in your salt. So here's your common strong acids. Those are your big six. Here's your strong base. You talking about group 1, group 2. The problem with the solubility issues of the group 2 metals, so not all of them will. However, you're going to learn in a later chapter that we can do something to the group 2s that will make them dissolve, okay? But that's going to be down like chapter 15, so let's not worry about it now. A weak elect will not completely dissociate, only about 1% of dissociation. So those are your weak acids and bases, ammonia, acetic acid. So if they're not this big 6 acid, all the other acids out there would fall under a weak electrolyte. Non-electrolytes are your covalent substances that are not acids. All right, they are dissolving, occurs, but the solute does not make ions and cannot conduct electricity. So pure water, your sugar will not, your alcohol will not, antifreeze and starch will not. All right, so this is kind of like what the purpose of section 4.5 is. We finally hit the main idea here. So this is solubility of ionic compounds. Soluble means it dissolves in water. Insoluble means it does not. And again, later on in chapter 16, we're going to learn that everything has some degree, but that's really later on, okay? That'll be in the spring. Solubility of a compound depends on several factors. It says basically, if a compound is more attracted to each other than the attraction of water, it will not dissolve, okay? We will do some math to show this later on in chapter 12 and what it truly takes to dissolve. So right now, you're looking at just the attraction. Does the solute have a greater attraction than the solvent solute? It will not dissolve. The opposite is true, it will dissolve, okay? So for now, guess what we got? We have a solubility chart, okay? So here it is. You do not need to memorize these. You'll be given the chart when needed, okay? But it is very helpful to like remember some of these. For example, every single group 1 ion and ammonia are always soluble. Always soluble. There are what? No exceptions. All nitrates and all acetates, guess what, are always soluble. There is no exception. All right, so that's why we would use silver nitrate. All right, sorry about that. Mr. Bowles had to say something. So anyway, we would use it, so silver nitrate, it dissolves, and then we can use it to make silver salts that are insoluble. So a very common thing like silver nitrate and sodium chloride. All right, why would we use silver nitrate all the time? Because you can make a solution with silver nitrate. So any cation will, when paired with a nitrate, will dissolve. Any cation paired with acetate will dissolve, okay? So usually your chloride, bromide, and iodides are soluble. Most of them do dissolve with these exceptions, okay? With silver, mercury 1, or lead. The lead chloride, lead bromide, lead iodide does not dissolve. Mercury 1 chloride, mercury 1 bromide, mercury 1 iodide does not, as well as silver. Most sulfates are soluble with the exception of these 5, okay? Strontium, barium, lead, silver, or calcium. It's considered insoluble, okay? So these are going to be your soluble ions. These are your always, these are your most of the times. Down here, these are considered usually insoluble. Notice this is hydroxide. Isn't that interesting? All right, so when you look above is what was a strong base. It said a group 1 and somewhat group 2 hydroxides. Your group 1s will always be soluble. Why? Because, or strong bases. Why? Because they're soluble. Why? Because of the solubility rule up here. All your group 1 hydroxides will dissolve. All right. So it says when they're paired with what we said, group 1 ammonium, they will dissolve. Sulfide, when they are paired with calcium, strontium, barium, the resulting compound is soluble. What does that mean? If it's paired with anything else, it is insoluble. All right, when hydroxide is with these group 2s, it's only a little bit soluble. And again, we can manipulate calcium hydroxide so it can dissolve, but it doesn't do it on its own without the manipulations. All right, most carbonates and phosphates are not soluble. unless they're paired again with a group 1. So this is why it's good to know group 1s. Everything will dissolve in group 1. All right, so carbonate and phosphate, if it's not grouped with a group 1, it is insoluble. All right, it will form a solid. Okay, all right, let's go to the next page. All right, so predict whether each compound is soluble or insoluble. So you might have to flip back and forth somewhat. So see if you can't figure out that solubility table, see how it works, and then when you are done filling out these 8, come back. All right, welcome. What about lead 2 chloride? Well, it's one of those exceptions, isn't it? It's insoluble. All right. Calcium nitrate, it's a nitrate. They're always going to be soluble. I don't care what it's paired with, it's soluble. Okay, nickel 2 sulfide. Well, hey, let's go back. Maybe you didn't remember that. Here, let's do this. So it says when sulfide is paired with calcium, strontium, and barium, the resulting compound is soluble. What did I tell you? Everything else is insoluble. All right, so what does that mean about nickel 2 sulfide? It will be insoluble. Well, lithium carbonate. Well, what do we know about lithium? I try to stress that big time. It is always soluble. I don't care what it's with. It is soluble. Is that true with all carbonates? No, 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 no. It has to be paired with a group 1 to be soluble. What about calcium, or excuse me, copper chloride? Is that one of the no-nos for chloride? It is not, so it is soluble. Barium sulfate. Most sulfates are soluble with a few exceptions, and guess what? Barium is one of those. All right, what about magnesium phosphate? All right, where do you find magnesium? Magnesium is a group 2. So is magnesium phosphate soluble or insoluble? It is insoluble. And then finally, ammonium is paired with anything, and it is soluble. Okay, hopefully that helped. And now in the next section, 4.6, we're going to see, going back to our, oops, don't know what happened here, but anyway, I don't, in section 4.6, we're going to go back to our balance equations, and now we're going to start predicting our products, but we have to know that those solubility rules in order to do that. So I'm going to leave you here with Don't Wait to Be Great, and continue on in 4.6. We'll see you next time. Bye-bye.